Welcome back to another week of online lectures. The topic of the first lecture this week is going to be geometric sequences. So as you might recall, last week we talked about arithmetic sequences and arithmetic series. So first of all, I just want to remind you what an arithmetic sequence is. So an arithmetic sequence is something that looks like this. So here's an example: 2, 4, 6, 8, etc. So the idea of this is that each number is the previous number with 2 added to it, right? So the sequence goes up by 2 at each position, and we call this a common difference, right, between any two successive terms. So this is an arithmetic sequence, and there's a common difference between successive terms. And we call that common difference D. Okay, so as it turns out, the idea of geometric sequences is actually very similar. So instead of there being a common difference, so instead of adding 2 every time, there's this idea that, okay, let's just give you an example. So let's go 2, 4, 8, 16. So this is an example of a geometric sequence. So instead of adding some common number every time, we multiply by some common number every time. Right, so each number in the sequence is the previous number times 2. So instead of there being a common difference, we call it a common ratio. R is equal to 2. And this is a geometric sequence. So there's a common ratio between successive terms. And we call that common ratio R. So when we say common ratio, what we really mean is that the next term divided by the previous term is always going to be 2. So that's why we call it a ratio instead of a common factor. So another way of saying that is if you're sort of okay with this kind of mathematical language, Tn plus 1 divided by Tn. So this is saying any term, right, divided by the previous term is equal to some common ratio R. So if that doesn't make sense to you, just forget about it. It doesn't really matter. The core idea is that there's a common ratio, so that we could always work out what the next term in the sequence is by multiplying by 2. Okay, so that's the idea of a geometric sequence. So what I want to do now is try to see if we can work our way to coming up with a definition of a geometric sequence. So let's work from this example up here. So we had this example 2, 4, 8, 16. Right, the first term in the sequence we're going to call A again. That's the first term. And then we know that our definition should probably have this factor, this common ratio of 2 in it, right? So let's think about this for a minute. So if the first term is A, if we call it symbolically A, right, our second term should be A times R, right? And then our third term should be, well, this one times R again, so that's A times R, which is the same thing as R squared. And the next one is going to be AR cubed, etc., etc., etc. Okay, so this is now getting pretty close to a definition. So what I'm going to do is now basically just write down what I want the definition to be, or what the definition is, and then we'll sort of work backwards and show that that's actually what we're getting here. So there's a definition that looks like this. Tn is equal to A times R to the power of n minus 1. Now why to the power of n minus 1? Well, that's because when we put in T1, we want to get A, right? So T1 is equal to A to the power of r times 1 minus to the power of 1 minus 1. So that's a r0, which is, you can plug this into your calculator, but any number to the power of 0 is always the number 1. So this gives us a. So that's why we need to put in that power of minus 1 there. So if you didn't follow that, again, it's not really that important, but I like to do it anyway. So, but the basic idea that you really need to get comfortable with is that this is the definition of a geometric sequence. So the definition, or you might call it the equation, of a geometric sequence. So the rest of the video really is going to be playing around with this equation and seeing what we get, or trying to generate that equation. So this is the definition of any geometric sequence. Right? All we need to do is plug in what the first term is, what a is, plug in what the common ratio r is, and then we can know what any term in the sequence is. Okay, so let's try to work with a couple of examples now, okay? So let's do the first kind of example that I want to do is show you how to generate some term in the sequence from a definition. So what I'm going to do is give you a definition. So give you an equation of a geometric sequence, and then we'll calculate what some term of that sequence is. So let's say I have the equation Tn is equal to 3 times 2 to the n minus 1. Okay, so this is the definition of a geometric sequence where the first term is 3 and the common ratio is 2, right? So hopefully you can see that. So this is a geometric sequence. And what I want to do in this example is use this definition here to work out what, say, T7 is. So what's T7? T7 is when n is equal to 7, right? So I can take this equation and plug 7 in everywhere where I see n and work out what T7 is. So T7, all I'm doing is plugging this in, is equal to 3 times 2 to the power of n minus 1, which is 7 minus 1. So I can simplify this as 3 times 2 to the power of 6. So now I can plug this into a calculator. 3 times 2 to the power of 6 is 192. Right, so the seventh term in this sequence would be the number 192. So that's reasonably simple, really. All we really did was take this equation and plug a number into it and get a number out of it. So that tells us what, that's what I mean when I say that this equation, this definition tells us what any term in the sequence is. So we found that the seventh one is 192. So now I want to move on to a different kind of example. And what I want to do now is give you a sequence, and then first of all work out whether or not it's geometric. And then if it is geometric, find the equation for it, or find the definition. Okay, so the sequence that I'll give you will be, let's see, how shall I do this? 1, 3, 9, 27. And what I want to do is, first of all, is this geometric? 2, if so, find the equation for it. Okay, so let's do 1. Well, we have 1, 3, 9, 27. So is there a common ratio here? Well, 1 times 3 is 3. 3 times 3 is 9. 9 times 3 is 27, right? So all these numbers are the same. So we'd say that there's a common ratio r is equal to 3. So we know there's a common ratio, so it is geometric. So that's good. So now we can move on to part 2. If so, what's Tn? Well, we know that it's geometric, right? So we set up here that for any geometric sequence, we can use this equation here. So we know that Tn has to be equal to a times r to the power of n minus 1, where a is the first term, and r is the common ratio. Now we've already worked out, right, that our common ratio here is r is equal to 3. We also know what our first term is, right, because we have the sequence. We know that our first term, a, is equal to 1. So I want an equation in terms of n, right? So we're going to leave the n in there because we want to be able to know what any position in the sequence is. So all I need to do is plug these two numbers into this equation to give us the equation of this particular sequence. So when a is equal to 1, right, that's 1 times r. r was 3 to the power of n minus 1. So 1 times any number is that number back again, so this thing is just 3 to the power of n minus 1. And that's it. That's the equation of that sequence that we were looking for. And we can't simplify that any further, right? Because now we know what the nth term is, and there's nothing else to simplify. And so we're done with that question. We have our definition. Tn is equal to 3 to the power of n minus 1. Okay. Now what I want to do is one more example. And I want to do a slightly trickier kind of example, where instead of knowing the sequence, we just know two terms of the sequence. So what I'm going to say is we have a geometric sequence where we know two terms of it. So we know that the first term is equal to, I'll just make it 1 to make it simple, and the third term is equal to 4. Now this is about as simple an example as I can think of for this kind of situation, but I want to kind of try to walk you through the process. So what I want to know is what's the functional definition or the equation for this. So what is Tn? Well, we said it's geometric. We said that the sequence is geometric, so already we know that it's going to have an equation that looks like this. Tn is equal to a times r to the power of n minus 1, right? This is the first term. And this is the common ratio. So what's Tn? Well, let's try to use these two bits of information in order to work it out. Okay, so we know T1, so we know what this whole thing equals to when n is equal to 1. So when n is equal to 1, we know that T1 is equal to a to the power of r n minus 1. But we know n is 1. Right, so r to the power of 1 minus 1 is r to the power of 0. Any number to the power of 0 is just 1. So this is a times 1, which is equal to a. Right, so all we really did there is work out that T1 is equal to a, which we already kind of knew anyway, right? Okay, so now what I can do is use this second bit of information. And we know also, that this is equal to 1, right? Because T1 we set up here is equal to 1. So now what I can do is plug this into the equation. So now we know, right, that Tn is equal to 1 times r to to the power of n minus 1, right? So we've got one of those pieces of information in here, and this we can simplify to r to the power of n minus 1. So now what I want to do is try to solve for r. Well, I can't quite do that yet, but I still have one more piece of information here, right? We know that t3 is equal to 4, and we know that t3 is equal to 1 times r to the power of 3 minus 1, right? Because we know that Tn is r to the power of n minus 1. Let's get rid of that. We know that Tn is r to the power of n minus 1. So now all I'm doing here is plugging 3 in to this equation for n. So T3 is r to the power of 3 minus 1, which is the same thing as saying T3 is r squared. So we know that T3 is equal to 4, and we also know that T3 is equal to r squared. So we know that r squared must be equal to 4. So this is an equation that we can solve now, right? We know that r squared is equal to 4. So what we can do is take the square root of both sides and get r is equal to, now we need to be really careful here. So we know that r squared is equal to 4. So this, as it turns out, actually has two solutions, right? So we know that r can be equal to 2 because 2 times 2 is 4. But it also actually has another solution. R can also be negative 2, right? Because also negative 2 times negative 2, negative 2 times negative 2, so negative 2 squared is also 4. So that's another possible solution for r, right? So now let's think about this. So we know that Tn, right, going back again, Tn we said was r to the power of n minus 1. And now we know that r is either 2 or negative 2, or actually both of those are solutions. So it's kind of weird, but when we gave this initial bit of information here, we wanted a geometric sequence where t1 is equal to 1 and t3 is equal to 4. What we found is that there are actually two possible solutions to that scenario. One of those is that Tn is equal to 2 to the power of n minus 1, right? And another possible solution is that Tn is equal to negative 2 to the power of n minus 1. And both of these are equally valid solutions to that problem that we started with. And like I say, I know that might be a little bit weird, but that's what actually happens. Okay, so I think those are probably all the kind of examples that I need to do. So I think that's it for this video, but I'll see you guys soon.